So let's finish up section 6.4. We've done this kind of stuff before. If you remember, we've already done this. Let me. So right here is a rectangle. Shh. Who started? No, not they. You. So watch. We already said if this is a rectangle right here, I didn't put the right angle marks, but it's a rectangle. Okay, what did we know about the diagonals of a rectangle? Well, they bisect each other because it's a parallelogram. But what's true about the diagonals specifically because it's a rectangle? They're equal to each other, correct? Girls, come on. I'm in the middle of something. Rose, there you go. You gonna go or what?
Yes. Enough. Full of my notes. I'll be probably on the only question I have. So God's true.
So we've said this before. We said that if you have a rectangle, if you know it's a rectangle to begin with, then the diagonals, they don't just bisect each other, which they do because it's a parallelogram, but they're actually equal to each other. They're exactly the same measurement, okay? Today's a little different. So what they're doing here is saying this. I'll tell you what, let's put some... Yeah, I didn't do this in my notes. I just wrote out the theorems, but let's do this anyway. I'll just wing it here. A, B, C, D. We'll call this E. Okay? So what this theorem says, and we've done this before, we said, remember if-then statements? We talked about if-then statements. We've done a lot of them. A lot of the theorems are if-then statements. If this is true, or if it's a parallelogram, or if it's a rectangle, then this is true. So we've already learned the theorem that said, if this is a rectangle, then the diagonals are equal to each other. Everybody hear me on that? Yes, so if I know it's a rectangle, what must be true about the diagonals? They must be equal. But let's say I didn't know this was a rectangle. I mean, it looks like one. What if I didn't know for sure, 100% that this was a rectangle? Okay, I got no right angle marks on here. I don't really know for a fact that it's a rectangle. But what if I knew? What if that I said AC was equal to BD? Then, what do you think I could say about this quadrilateral right here? If I knew that the diagonals were equal to each other, what do you think I could say about that quadrilateral, John? Yeah, then it would be a rectangle, okay? So if the diagonals, okay, of, they say a parallelogram. I think you might even be able to say a quadrilateral. But if they say, if the diagonals of a parallelogram are equal to each other, then what is this thing? It's not just a parallelogram. It's a what? It's a rectangle. So that's basically what the theorem says right there. So if the diagonals are equal to each other, then this would be a rectangle. Everybody with me on that?
Yes,
it's a subtle difference. Do you see the difference? We talked about this before, and we've said this exact same thing before. It's a subtle difference, but it is a difference. Again, we don't know that it's a rectangle to begin with, but if I could show you, if I knew that AC and BD were exactly the same, then what could you tell me about that four-sided figure? Then you could say it's a rectangle. Then you could say for certainty that angle A was 90 degrees, angle D, angle B, angle C were all 90 degrees. Everybody got that?
Yes, sir.
Okay. So let's move on. What if I had this? It's not going to be a square. Looks like a square, doesn't it? But I'm going to hit the shear button. I don't know, let's go to like 20 degrees. Now, again, we're going to do the same thing with this. We've talked about this before. Again, we've talked about the diagonals of this thing before. Now, all four of these sides are equal to each other. I'm telling you right now that they are equal to each other. So what do I call that big figure right there? All four sides are equal. It's a rhombus. It's not a square. Okay, we don't know it's a square. Just because all four sides are equal does not mean it's a square. Now, it could be a square, but it doesn't mean it has to be a square. What does it have to be if all four sides are equal? It has to be a rhombus. It's got to be a rhombus, okay? But just like the other one, we're not just going to assume this is a rhombus, okay? But we're just kind of backtracking a little bit. If this was a rhombus, if all four sides were equal to each other, what do those diagonals do? Something very specific that only happens on a rhombus, and it doesn't happen with a rectangle, it doesn't happen with every parallelogram. It only happens when it's a rhombus. What do those diagonals do to each other if this was a rhombus? They're perpendicular to each other, absolutely. Okay, good. So these diagonals right here are perpendicular to each other if it was a rhombus. Okay, but what are they doing now? They're doing the opposite. They call it the converse, okay, by the way. So if I switch the if and the then, if I say, again, let's label it. We'll use the same letters. Okay, so if, let's see, AC is perpendicular to BD. Now, I didn't say they're equal to each other, okay? They're perpendicular to each other. If they're perpendicular to each other, what then could I say about that whole four-sided figure right there? I could say that it's a what? It's a rhombus. Then you could put it's a, but I'm just going to shorten it, just put then rhombus. You see the difference? Right now, I don't know for a fact that it's a rhombus, but somebody told me that that is a right angle right there. So if I know that this is a right angle right here, that means these two lines are perpendicular to each other. These two line segments are perpendicular to each other. So that means they're perpendicular. If they're perpendicular, what does that mean about this whole thing then? Then it's a rhombus. Okay? You see the difference? Okay. Because again, before the old theorem said, if it's a rhombus, then the diagonals are perpendicular. This one says, if the diagonals are perpendicular, then it's a rhombus. Okay? So let's say that's the only information they gave me about this picture right here. That's all they gave me, is that that's a 90-degree angle. And I said this was 5. Could you tell me what AD is equal to? I guess we're not getting it. If I gave you this information right here, I said that this is a right angle right there in the middle, okay? And that's all I told you, except I told you that that side right there is 5. Tell me what the length of AD is going to be equal to. Why? It's not just a quadrilateral, it's a what? It's a rhombus, that's right. Because if they're perpendicular right here at E, if they're perpendicular, then this thing's got to be a rhombus. So if this side is 5, then what's this side? Then all the other sides are going to be 5. That's right. All the sides are equal because a rhombus has all equal sides. Everybody with me on that? Okay. So that's the kind of stuff they could do. Obviously, they could make this a little harder. They could put like this is like 2x minus 1, right? And then this is 3x plus 2 or something like that. And then what would you do? You'd set them equal to each other, solve for x, plug it back in, and then you could get the length. Then you could get the length of these segments right there. So I just made it as easy as I could. You obviously know that they're going to put some variables in there and all that kind of stuff. You have to solve for x, do some algebra. We've been doing that all year, and I've been saying we've been doing that all year. All right, here's another one. So that's 2 of them. Let's do another one. Let's say it's not necessarily a rhombus, and it's not a rectangle. So let's kind of just shift this a little bit. That's good enough right there. Okay. I'm sorry. I can't make it look like that. Let's try it again. Oh, come on. There you go. All right, now let me try to, I'm going to make it into another, what looks like a rhombus. Okay, here we go. Let's put some parallel, or let's put some diagonals in here as well. Okay, so actually, let's just put one diagonal. I'll tell you right now, I drew this as a rhombus, okay? What did we learn just pretty recent about what a diagonal does to the angles right here? If it's a rhombus, it bisects, exactly right. So if this is a rhombus, this diagonal bisects these opposite angles. So for instance, what if that whole big angle, we'll make it easy, we'll say it's 60 degrees. What if that whole big angle, that can't be 60 because that's an obtuse angle. Let's say it's 120 degrees. Let's say that whole big angle is 120 degrees. If this was a rhombus, this is a diagonal, so what would be true about this angle right here and this angle right here? Say it, John. Well, the whole thing's 120. The whole entire angle is 120. What would this little angle right here be? It'd be 60 degrees. Right. Yeah, it's kind of in... There you go. Sorry about that. All right, so this would be 60, right? And this would be 60 because it's bisected. All right, so a diagonal bisects the angles of a rhombus. Everybody hear me? That's something that we've learned in the past. Okay? But let's change what we know about this. Let's say we don't know it's a rhombus right now. I don't know that all four of those sides are equal to each other. Okay? They're not marked equal. I'm not saying that it's a rhombus. But let's say that this angle was 60 degrees. And let's say this angle is 60 degrees. And then I asked you, I'll say that side is 7. And I asked you for the other 3 sides of this thing. So now watch. We have a diagonal that bisected an angle. So we said, if a diagonal bisects an angle, okay, of this parallelogram, then what kind of figure is this? We said at the beginning, we said, if this is a rhombus, then the diagonal bisects the angles, right? So what if we go the other way? What if we say the angles are bisected? So if the angles are bisected, then this figure is a rhombus. That's right. Okay? So if you bisect this angle, I don't know. I didn't tell you it was a rhombus, okay? I didn't say that all 4 sides are equal to each other. I just said that this diagonal bisects this angle right here, which makes it 2 equal angles, right? If I know that, then what do I know about the whole entire figure? I know that it's a rhombus. So if this side is 7, just like we did on the last one, then what's this up here? That's, well, it's a rhombus, so this side, the length of this side is what? It's 7, and this, all the sides are 7. That's right. Okay? Everybody with me on that? All right. We got one more of these kind, then we got another different type of theorem, and then we'll be done. I'm going to just copy this one so I don't have to do that whole shear thing. All right. Here's another thing right here. Two consecutive sides of a parallelogram are congruent. All right, here we go. This one should have been the first one. This is probably the easiest one. So what if this was 5 and then this was 5? So if I have a parallelogram, listen, I'll tell you what, let's do, let's just make this a little bit smaller so I can fit something else in here. Okay, and let's make this a little smaller. And let's stretch this out. Whoops. Come on. Here we go. All right, watch this. I'm going to show you 2 different things here. Okay, I made this to look like a rhombus. Okay, so here's the thing. I can't remember actually. Did we even teach the other? I don't remember even teaching this other thing earlier, but I'll have to look back and look at it. But here's the thing. Here's what it says. It says if 2 consecutive sides. What does that mean, consecutive sides? It means the ones that are right next to each other. It doesn't mean the opposite sides. Everybody's watching up here, right? Not everybody is. Some people aren't even paying attention to anything I'm saying. Shh. So watch. If I know that these two sides right here, they're called consecutive sides because they're ones right next to each other. They're not opposite sides, okay? They're consecutive sides. We had a theorem that for some reason I can't even remember doing, but we had a theorem that said if you have a rhombus, then the consecutive sides are equal to each other. So what if the consecutive sides right here were equal to each other? Then what must this thing be? What must this parallelogram actually be? It must be a rhombus. So if these two, if they give you that this and this are 5, what do you know about these two sides right here? Then they got to be 5 as well because it's a rhombus, all right? Because all 4 sides are equal to each other. Notice the difference. What if this was 4 and this was 5? Do you see the consecutive sides are not equal to each other here? So there's no way this could be a rhombus. First of all, it can't be a rhombus because the two sides are different, right? So in order to be a rhombus, all the sides are equal. But what was given to us? It was only given that this and this were equal. If we know that information, then this side and this side will also be equal to each other. All right, enough of that. Let's do one more thing, and we'll be done. So I'm going to put a couple parallel lines here. And I'll just put a little arrow right there. What does that arrow mean? Does that mean it's a line? It means they're parallel to each other. The little arrows on the ends, right, they mean that it's a line, okay? This arrow and this arrow right here means that they're parallel to each other. Now, what if, we've talked about this before. Remember we talked about you're up in an airplane, you want to find the altitude, right? All right, that's the distance. Yeah, you go, instead of saying straight down, a lot of people say straight down, but after you took a geometry class, you wouldn't say straight down, you would say what? Perpendicular, right. You'd say perpendicular. So watch. What is the distance from this point to this line down here? It is the altitude, that's right. But is it from here to here?
No.
Is it from there to there?
No.
Where is it? From the point where? Give me a word. Give me the math word. We said it just like 5 seconds ago. Perpendicular to the other one, okay? All right, so that right there, I'll call it D for distance. That would be our distance, or you could call it the altitude, right? That's exactly what it would be, right? From a point perpendicular to another line, that would be the altitude, or that's the distance, okay? So what if I came over here and I found another point? What's the distance from this point to this line? Is it from here to here? Is it from there to there? Is it from there to there? What is it? It's not a trick question. It's perpendicular, just like we said before. Okay, it's perpendicular. You guys are looking at me like I'm trying to fool you, but I'm not. Okay? So, now watch this. If this is the distance from a point on one parallel line to the other parallel line, what do you think is true about both of these distances? That they are equal to each other. So if this was D for distance, what would this be? That would be D as well. I could keep doing that forever and ever, couldn't I? Okay, I could take another point from that perpendicular line. And as long as I go what? Perpendicular, then what's true about all of these distances? They're all equal to each other. So the theorem says this. You can write it down if you want or look in the book. It says 2 parallel lines are everywhere equidistant. If you think about it, it should make sense, right? If I have 2 lines running parallel to each other, let's take the floor and the ceiling, okay? If you look at the floor, you look at the ceiling, if there was a point on the floor, I would say, what is the distance from that point to this floor? Where would you measure it? You would measure it what? Perpendicular, right? Okay, some people would say straight down, and I know what you mean by straight down, but technically it's perpendicular, right? So take a point anywhere else on this ceiling, okay, and find the distance from that point to the ground. What would be true about both of these distances? They should be the same, as long as the people who built the building, right, made the ceiling parallel to the floor. Now, if the floor was slanted, that'd be a different story. So that means they wouldn't be parallel, correct? Okay, So as long as the lines are parallel, the distance from one line to the other are going to be the same throughout the whole entire thing. If they were not parallel and this was slanted up a little bit, then this distance is going to be shorter than this distance. Agreed? All right. So as long as they're parallel, the distances are exactly the same. It's a pretty simple concept. Nothing super difficult about it, but you might have a couple questions with that. All right. Now, this, I got to be honest with you, this scares me a little bit. Because you got about 17 minutes left, and I'm going to let you work on your homework, okay, with the next 16 to 17 minutes. So I gave you the lesson plan already today, but I'm going to write it down just in case you need to look at the YouTube video to remind yourselves what the lesson is. So it's 272, 273. That right there is your homework.